Hi class, we continue our study of series and sequences talking about absolute convergence and what we call the ratio and root tests. All right, so let's first talk about absolute convergence. So if you're given any series, summation a sum n, we can consider the corresponding series. So by looking at the absolute value of the sum of the individual terms, okay, whose terms are the absolute value of the terms of the original series. So we're going to consider this. So what we say here is a series, summation a sub n, is called absolutely convergent if the series of absolute values is also convergent. All right, so if we take the series and look at the term, the absolute value of the terms, and it's convergent, then what we can say is the original series is absolutely convergent. All right, so note that if the series here, summation a sum n, is a series of positive terms, then we don't really need to show the absolute value because the absolute value of a sub n is just equal to a sub n. And so absolute convergence is basically the same as convergence in this case. All right, so let's consider this series here. If you look at it, the sum from 1 to infinity of -1 n minus 1 over n minus 2, or excuse me, n minus 1 divided by n squared, sorry for that misspeak there, is equal to, and this is what the expansion looks like here. Well, this is absolutely convergent because if you take the absolute value of the terms, all right, this sum, when you take the absolute value, is just equal to the sum of 1 divided by n squared, which is a convergent p series because p is equal to 2. So when you go, sorry to go back. So because this is absolutely convergent, it is also convergent. All right, let's look at this one. We know that the alternating harmonic series, if you look at -1 to the n minus 1 divided by n is equal to this, when you expand it out, is convergent. But here's the thing, it is not absolutely convergent because the corresponding series of absolute values, if you take the absolute values, you just get the sum of 1 over n, right? Which is a harmonic series, all right, or a p series of p is equal to 1 and is therefore divergent. Right? So you can be convergent, but not absolutely convergent. All right, just a couple definitions. So a series, the sum of a sub n, is called conditionally convergent if it is convergent but not absolutely convergent, like this case right here. All right, this is conditionally convergent. So example 2 shows that an alternating harmonic series is conditionally convergent. Thus, it is possible for a series to be convergent but not absolutely convergent. However, our next theorem here shows that absolute convergence implies convergence. So if a series A sub n is absolutely convergent, then it's also convergent. Right? Notice how it works that way, but not the other way. Let's look at this one. So determine whether this series, the summation of cosine of n over n squared, which equals, as you can see, expanded out, is convergent or divergent. Well, the series has both positive and negative terms, but here's the thing, but it is not alternating. So the first term is positive, the next three are negative, and the following three are positive. All right, so what's going on here is the signs change irregularly. All right, so we can apply the comparison test to the series of absolute values. All right, so if you take the absolute value, you don't need to worry about the squared because it's always squared. So you get the summation of n is equal to 1 to infinity of the absolute value of cosine of n over n squared. Right? And since cosine of n is less than or equal to 1 for all n, this is what we have. Right? So the cosine of n divided by n squared is always less than 1 over n squared. We know that the summation of 1 over n squared is convergent because it's a p series with p is equal to 2. And therefore, the absolute value here, the summation of absolute value of cosine of n divided by n squared is convergent by the comparison test. All right, thus the given series here is absolutely convergent, and therefore it's convergent by that theorem 3. All right, so about absolute convergence here. So the following test is very useful in determining whether a given series is absolutely convergent. And this is what we call the ratio test. And it looks at the ratio of the limit as n goes to infinity of the nth plus 1 term divided by the nth term, okay? And it's 3 different cases. All right, so if you take that limit and the limit, all right, is equal to some value L, so it exists and is less than 1, then the series is absolutely convergent. If the ratio of the limit of the ratio of the n plus 1 term divided by the nth term is equal to L, so its limit exists but it's greater than 1, then it's divergent. And if that the limit of the ratio is equal to 1, it's inconclusive. You can't draw any conclusion. All right, so let's take an example of this. All right. So note in part 3, the ratio test says that if the limit as n goes to infinity is equal to 1, the test gives no information. So for instance, for the convergence series, all right, so we know it's convergent. The summation of n, summation of 1 divided by n squared we have. So the nth plus 1 term is 1 over n plus 1 squared, divided by the nth term, 1 over n squared, which simplifies to the following, which when you take the limit of this, right, simplified even a little bit more by dividing by n squared. When you take the limit of this, like so, it goes to 1. So as n goes to infinity. So even though the test is convergent, the ratio test doesn't tell us if it absolutely converges, right? Because here it's equal to 1. All right, well, let's look at this divergence series here, all right? So we have this divergence series, the summation 1 over n. If you go through the same process here, looking at the absolute value of the ratio of an plus 1 divided by an, I'll let you go through the algebra here, but you see that this limit just goes to 1 as n goes to 1. So therefore, this limit, all right, is equal to 1. The series a sub n might converge or it might diverge. We don't know. In this case, the ratio test fails and we must use some other test. All right, let's look at this one. Let's test the convergence of this series. So the summation of n is equal 1 to infinity of n to the nth power divided by n factorial. All right. Since the terms a sub n are all positive, we don't need to use the absolute value signs. Like back here, it's always the limit of the absolute values. We don't need to use those absolute value signs. So when we look at this, a sub n plus 1 is this factor divided by, so I just flipped this, all right, so because when you divide by a fraction, it flips. So when you simplify, it looks like this. Continuing more, you'll see that this cancels with this cancels with this, and then you're just left with n plus 1 divided by n to the nth power because you have n plus 1 to the nth power and n to the nth power left, right? Simplifying here, splitting the fraction, n over n is 1, 1 over n raised to the nth power. Well, this, as the limit goes to infinity, is just e. So since it's a number, it's like 2.71, the given series is divergent by the ratio test. All right, so although the ratio test works in example 5, is an easier method for this is to use the test for divergence. So since we can see that a sub n, which is n to the nth power divided by n factorial, is equal to this, which is definitely greater than or equal to just n, it follows that a sub n does not approach 0 as n goes to infinity. So therefore, the given series is divergent by the test for divergence. All right, let's do one more test. All right, so this is called the root test. So the following test is convenient to apply when nth powers occur. So if you take the limit as n goes to infinity of the nth root of the absolute value of a sub n, and it equals to L, well, if that's less than 1, then the series is absolutely convergent. The same deal if that limit is greater than 1, right? Or it goes to infinity, then the series is divergent. And then if that limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to 1, all right, just like the ratio test here, the root test is inconclusive. All right, so if this limit equal 1, then part 3 of the ratio test is the test gives no information, so the series could be convergent or divergent, all right? So if L is equal to 1 in the ratio test, don't try the root test because L will be 1 again. And if L is equal to 1 in the root test, don't try the ratio test because it will fail too. So just remember that. So if they equals 1, don't try another test. So let's look at this one. Let's test for convergence here. All right, so I have something to the nth power here. All right, so I don't know if this is going to converge or diverge. So take this here, take the nth root of the absolute value. Well, the nth root just gets rid of the n here because you take the nth root, the n cancels. Well, when you take the limit as this goes to infinity, all right, it's just equal to 2/3, which is less than 1. So thus the given series is absolutely convergent and therefore convergent by that root test.